So typically I would just have everybody pick up their quiz at the end of class, but the grader put the scores on the front, so I'll just hand them back to you. I don't share your scores with everybody. Okay. Zoe here. Yeah. Paris. Garrett. Jen. That's not here yet. Anson. Oh. Sorry. Okay. Anson. Adam. Stephen. Samuel. Justin. Sharon. Min. Eva. Joel. Georgia. Dennis. Frank. Natalia. Sarah. Here. Brianna. Sebastian. Yeah. Queen Bun. Kevin. Kyra. Haley. Emma. Dominic. Jerry. Griffin. Ryan. I think this says Isham. Isham. Ishuen. Shuen. Isaac. Ellen. Kyle. Tyler. Back to Zoe. Okay, great. So, Mike, you ready to start? Oh, no, there's plenty of time. Who doesn't have their quiz back yet? Okay, what was your name again? Dennis. Dennis, okay. Okay, who else? What was your name again? Paris. Paris. Okay. Everybody have their quiz back here? Good. Right. So I'll say this again when everybody's here, but there's a 12-point curve on the quiz. Right. So don't be too discouraged or worry too much at the numerical value on your paper. Right. I'm going to upload that information to Canvas after class. I'll actually put your scores in the site, and that will be with the curve. Okay. Right. So people who are just coming in, I was just passing the quiz back. Usually I would just have you pick it up, but all the scores are on the front. Georgia. Okay. again? Joel. Joel. Eric? Isaac. Isaac. Oh, I think, yeah. Oh, difficulty reading your name. Hey, can you remind me of your name again?
Haley.
Haley. Right, okay. Here you go. Sorry, could you just remind me of your name? Oh, Tyler. Tyler. Sorry. Eva. Okay. Sorry, could you just remind me of your name?
Isha.
Okay, so we should start. If you didn't get your quiz back already, give me after class. I'll hand it back to you. So let's not forget that we'll have a quiz tomorrow as well. Quiz tomorrow. Covering everything through today. That is since the last quiz, right? No, it's not cumulative, right? It's just what we've done last Thursday up to today. Okay. Right. So about the quiz that I've just handed back to many of you. There'll be an additional 12 points added to all the scores, right? I didn't bother writing that on the actual your actual papers, but when I upload the scores tonight to Canvas, that will be reflected there. Okay. Good. So let us recall where we left off. We were talking about bounding certain improper integrals to determine if they converge or not, right? Which is, well, maybe not the most information we could have, but still can tell us some useful information. And I ask you to think about what we should do in trying to determine whether or not the following integral converges. 1 plus sine x divided by root x dx. So what do we think here? Well, let's just do our basic analysis first. That is to say, what is the behavior of the integrand like? Where is it defined and where is it not defined? Specifically in regard to the domain of integration. Yeah.
It's undefined at 0.
It's not defined at 0 and perfectly fine everywhere else in the domain of integration, 0 to 1, right? In particular, we have an asymptote at 0, right? So, good. how, if at all, can we compute the antiderivative of this integrand? Is there anything easy that we can say about this? It's one of the forms of antiderivatives that we recognize from our investigations last week. Maybe. Not really anything we can do with this. That's easy. So we should decide if we want to bound it from above and see if something converges, or have something bounded by this and show it diverges. What do we think? Well, let me just record this. Okay, so no easy antiderivative. So let's try bounding. Okay, well, forget if we want to bound above or below. What can we say about the behavior of the numerator of this function? Let's just talk about bounding the numerator on its own. Remember, the range of sign is from -1 to 1, right? So that tells us something about how we might bound this function, right? So what can we conclude from that? Yeah.
It won't be more than like 2 and then not or 2 or 0.
Yeah. The numerator has a maximum value of 2 and a minimum value of 0. Okay, so let's record that. Due to the behavior of sign, we have the following string of inequalities. 0 is less than or equal to 1 plus sine x divided by root x is less than or equal to 2 divided by root x. Okay, so instead of just trying to make a blind decision about whether we should bound above or below, just by analyzing the behavior of this function, we get a natural situation where we're bound above. Okay, so now we want to instead investigate the improper integral from 0 to 1 of 2 divided by root x dx. Okay, so it's from our definition of improper integral. The limit as a approaches 0 from the right of the integral from a to 1 of 2 divided by root x dx. Okay, what's the antiderivative of 2 over root x? I'm sorry, say that again. So remember, yeah, the antiderivative of 1 over x is ln. This is a power rule, right? So I guess I could rewrite this slightly to make that more transparent. Integral from a to 1 of 2 times x to the -1/2 dx. Okay. Okay, so now tell me what the antiderivative of this is. Yeah.
4x.
Yeah, good. So we get 4x raised to the 1/2 power evaluated at 1 and a. take the limit as a approaches 0 from the right of 4 minus 4 times a to the 1/2. Okay. So how do we evaluate this limit? Polynomial in a, right? So we just plug in 0. So our bounding integral converges. So we can conclude that the original integral we were interested in, 1 plus sine x over root x dx is less than or equal to 4. So it must converge. Right. So just one note about this. When we produce our bounding function, notice that I said, let's just look at what happens in the numerator. We want to keep the same pathological behavior in the denominator of our bounding function, right? We want to preserve the fact that we have an asymptote at 0 so that our definition of improper integral makes sense for the bounding integral that we're trying to keep. Okay. Good. So now we'll begin to discuss the foundations of kind of the crowning result of the course, which is eventually we will be able to determine when and to what degree of precision we can approximate a function to the polynomial. So the first step towards doing this will be to try to approximate some of the simplest functions we know, namely polynomials themselves. Okay, so let's discuss how we approximate polynomials. Okay, so I want to consider the polynomial p of x equal to 4 minus 2x plus 5x squared plus 9x to the 5th. Now, of course, you probably are used to seeing polynomials written in descending order of powers. It'll become apparent why I read it this way very soon. But in reality, it's immaterial what order you write them in, right? Addition is commutative. There's a reason for this. We'll soon see. Okay, so some comments. When x is close to 0, higher powers of x are yet closer to 0. What do I mean by close to 0? Well, in order for this statement to hold, what I really mean is x is less than 1, right? Successive higher powers of a number less than 1 is closer and closer to 0, right? Okay, so excuse me. So just taking this observation, I can say a proposition. So if we have integers m and n greater than or equal to 1, then the absolute value of x to the n is strictly less than the absolute value of x to the m. And furthermore, the limit as p approaches 0 of the absolute value of x to the p, I'm sorry, as p approaches infinity, not 0, is equal to 0, right? Successively higher powers of a number less than 1 will get closer and closer and closer to 0. Okay, so what this means we can approximate a polynomial at values of x close to 0 by simply forgetting higher degree terms. Right? That is to say, if we're pretty close to 0, we can leave off the 9 times x to the 5th term and still get a pretty close to correct value, depending on how close to 0 we're talking about, right? We're going to get to the point where we make close precise, but for now, just think of it as being near 0. Okay, so here's some notation before we proceed. Right. A polynomial of degree n let's call it p of x again. And if we take m to be some integer greater than or equal to 0, right? P raised to the m power of x is just equal to the sum from I equals 0 to m of a sub I times x raised to the I. Or if you like, get a 0 plus a 1x plus a 2x squared plus a mx to the m. So let me make a couple comments about this. First of all, are we all comfortable with summation notation? This capital sigma, and we just let our index I go from 0 up to m. That's where I'm coming up with each of these terms in the sum down here. Yeah, this is okay. Okay. Secondly, this makes transparent why I chose to write this example polynomial from constant term, linear term, quadratic term, quintic term, right? Because this is the typical way of writing summation notation, right? You go up in index. Okay. So furthermore, for m greater than or equal to n, remember n is the degree of our general polynomial p of x over there. P raised to the m of x is just the whole polynomial p of x, right? So that is to say, if we choose m to be greater than the degree of the polynomial, hypothetically, we would have more terms than in our sum than the original polynomial had. That's okay. We just make those coefficients 0. Okay. So the only way that this is actually meaningful, this notation, is when m is greater than or equal to 0 and less than n. Right? The result there is we're just chopping off the terms of degree greater than m and less than or equal to n. Okay, so let's now return to our specific polynomial. Okay. So we have our polynomial 4 minus 2x plus 5x squared plus 9x to the 5th. Then let us just write down some of these truncated polynomials. So what do we get? P0 of x, I just take the 0 degree term of the polynomial and discard all the rest. The 0 degree term is just the constant term, right? So P0 of x is just the constant polynomial 4. P1 of x, it's 4 minus 2x. P2 of x equals 4 minus 2x plus 5x squared. What's P3 of x? Yeah.
It's the same as P2.
Yeah, it's the same as P2. Because there is no third degree term, and we discard everything of degree higher than 3, which is just this last term. What's P4 of x? Yeah. Good. What's P5 of x? It's just P of x. Good. So now let's actually make some calculations with this, right? Oh, I should, I said this in passing, but maybe I should write it down. These polynomials are truncations of our original polynomial P of x. Truncation, I believe that's from Latin, just for cut part of it off. Okay, so let's examine what happens at x equals 0.1. At x equals 0.1, what do we get when we evaluate each of these polynomials at this point? Well, P0 of 0.1 is just 4, the constant, right? P1 of 0.1 is, if you plug this in, you get 3.8. Okay, so P2 of 0.1 gives us what? 3.85.
Now, since P2, P3, and P4 are all the same, I'll skip right ahead to P5, or the actual value of the polynomial. Oops, not X. Right, take the time to make this calculation. What do I get? 3.85009. Okay. So this might not seem all too fantastical, but I can get pretty close just by computing only square things, right? That saves me a lot of time computation-wise. And when I say time, I mean like the time it takes a computer to run a program, right? The steps, the number of steps that you have to execute. Yeah,
I'm so confused here about the 0.1.
I'm sorry.
Where'd you get the 0.1 from?
I just picked it randomly as a point that's close to zero, a value of X that's quote unquote close to zero.
And it's only close to 0 because it's bounded, or because it's bounded to 0 or because of.
So nothing in the notation has anything to do with specific value of X. This is just from our discussion here, right? That for these X's that are close to 0, that we have this property that we can discard higher and higher powers of the polynomial.
You're not always going to choose a number close to 0. Maybe.
Well, we should continue with this example and see what happens if we get closer to 0 or further away. Okay. Okay, good. Let's look even closer to 0 at X equals, what did I choose here? Let's just put another 0 after the decimal point. So let's see here. P0 of 0.01, 4 again, constant. 1 of 0.01 is equal to 3.98. 2 of 0.01 is equal to 3.9805. And P5 of 0.01, which is the actual value of the polynomial at this point, 0.01, is 3.9805. Let's see here. 0, 0, 0, 0, 0, 9. Okay, so let's take stock of what happened here. We moved considerably closer to 0 by a factor of 10. And look at the dramatic increase in the accuracy of our approximation when we're looking at the second truncated polynomial. The polynomial of degree 2, I guess, is the term. So yeah, the point is that the closer that we get to 0, the more accurate our approximations become. And the further away from 0, the less accurate they become. So why does 0 possess this special role? That is to say, what if we wanted to approximate a polynomial near a different point besides 0? Well, we can do that. We just have to do a little algebraic manipulation and put our polynomial in a form that has the point at which we're interested encoded into how we write the polynomial. Okay, so let me be a little more explicit here. So definition. A polynomial centered at A is given by d of x is equal to the sum from I equals 0 to n of d sub I times, now not just x to the I, but x minus a
Raised to the I power. And then just as before, you may write
b0 plus b1 times x minus a plus b2 times x minus a squared all the way up to the n times x minus a raised to the n power. Okay, so right, some more terminology and definitions. The Dth order partial sum which we denote GD of x is the sum of the first D terms of G. G of x. Right? This is just as we wrote before, right? In our example. The sum from I equals 0 sorry, some of the first D plus 1 terms, right? Because we start at 0. Okay, so right, same exact format. All we've changed is the index. Okay, and again, if D is greater than or equal to n, then GD of x is just G of x. Okay. So now we would like to quantify exactly how accurate an approximation we make is. How do you think we could go about doing that? Any thoughts? How do we tell how far apart two things are?
He's like percent accuracy thing. He's like subtraction.
Yeah, subtraction, right? We subtract the actual value of a function from our approximated value. Okay. So, right. So let's take, well, been using G. Let's continue to use G. G of x, a polynomial centered at A. then the difference. I'll write this on the next board. The difference g of x minus gd of x, which will give a name rd of x, is called the d remainder. Okay, so finally, the error in approximating. G of x by gd of x is given by d of x is just the absolute value of the d remainder. Okay, so that is just quantifying the size of the error. We don't necessarily care about if it's an over or under approximation. Okay. So just one implication of this is that so GD of x approximates g of x within plus or minus the error. Okay, so let's write that in symbols. That is to say, dd of x minus ed of x is less than or equal to g of x is less than or equal to gd of x plus the error, the d error, I should say. Okay, so let us now put all these definitions together and see what we can say in an example. So let's let q of x be equal to 7 plus 3 times x plus 2 minus 5 times x plus 2 to the 4th. Okay, so before we go any further, what's the center of this polynomial? It's -2, yeah, because we subtract from x the center. So we're adding something. That means the center must be -2, right? The polynomial let's suppose that x is within 0.1 of -2. Let me ask you, what is the maximum amount of error that we could have? In approximating q of x by q1 of x. Okay, so we want to kind of unpack what this means. Yeah. Where do I start here? What information do I extract from this problem first? Well, here's one thing we can say. Let's analyze this phrase. What this box phrase implies is that -2 minus 0.1 is less than or equal to x, which is less than or equal to -2 plus 0.1. Yeah, that's just a translation from English into math. Okay, so now we're going to do some manipulation of this string of inequalities. Yeah,
Is that the same thing as the equation at the top there?
at the top. No. Remember, because there's the equation at the top, or actually the string of inequalities at the top. We're evaluating our what's the term? I just wrote it down over here. What is wrong with me here? Yeah, the dth order partial sum. We're evaluating the dth order partial sum at some x, right? And yes, also the error and the original polynomial. Here we're just bounding x, the input of the function, right? Okay.
So
Well,
that might
eventually
be
we're
the first-
getting there, right?
But eventually we will come to this. Yeah.
Like, the whole point is to go through to get to that.
Yeah.
So this is like the first step, just bounding it like that.
Yeah, right. So we're just taking the information that we're given and turning it into something that we can manipulate with calculations.
Oh.
Good. Okay, so I'll just add 2 to every part of this string of inequalities. Yeah. So this is the case. If and only if -0.1 is less than or equal to x plus 2 less than or equal to 0.1. So now we're getting a little closer here, right, to something that resembles our polynomial. We actually have the an expression with the center in it now, right? Okay. So this is the case if and only if. Well, as a matter of fact, how can I rewrite this string of inequalities into a single inequality? I have some quantity that is bound below and above by the same number, except for sign, right? This is negative and this is positive, but it's both 0.1. Then I can express this as an inequality using absolute value, right? This is the case if and only if the absolute value of x plus 2 is less than or equal to 0.1. Okay, remember this, like unfolding an inequality with absolute value? Yeah, okay. So the error in approximating qx by q1 of x is given by, well, this is just our formula. E1 of x, right? This formula here is equal to the absolute value of R1 of x, the first remainder, which you'll recall is the absolute value of this difference that we defined the remainder to be. And now we can actually come up with an expression for this, right? What is our q of x? 7 plus 3 times x plus 2 minus 5 times x plus 2 raised to the 4th minus q1. What is q1? So here's our q. How do we calculate q1?
7 plus 3 x plus 2.
Yeah, right. We just take these first two terms, right? Okay, so 7 plus 3 times x plus 2. Okay. In other words, the absolute value of -5 times x plus 2 to the 4th, which I can just pull the -5 out and -5 is an absolute value times the absolute value of x plus 2 raised to the 4th. Yeah. Okay. So altogether, so if the absolute value of x plus 2 is less than or equal to 0.1, which was our first deduction, right? The upper bound on approximating, or sorry, on the error of approximating q of x with q1 of x given as follows. U1 of x, we just derived a formula for, right? 5 times the absolute value of x plus 2 raised to the 4th, which must be less than or equal to right? Because of this inequality. 5 times 0.1 base to the fourth, which is equal to 0.0005. Okay, so how do we interpret this? What information is this telling us? It's saying that for this polynomial, q, if we stay within 0.1 of the center, -2, this is the most we'll be off by in making an approximation. This error, plus or minus this. Okay. So I mean, this is perhaps not so surprising, right? Because there are no terms between the first degree term and the fourth degree term. So when we're very close to our center, the remaining part that we chop off in producing Q1 contributes very little to the total value of Q for any of these x's that are within 0.1 of -2.
For other question was, you had a different polynomial, did you just subtract the exponents and multiply by the coefficient that's an answer, or is this one just work out this way?
That's a coincidence. Yeah, good observation, but yeah, we built all this machinery for a reason. Yeah, good. Okay, so okay, so what happens if we're given some polynomial and we want to change its center so that we can approximate its value at a different point than the center that we're given? How should we proceed in doing that? Well, let's try to work out an example and see if we can say anything general after we do that. Okay, so let's return to our polynomial that we started with, p of x equal to, actually, let me write this on the next line. P of x is equal to 4 minus 2x plus 5x squared. Okay. Yeah. Plus 9x to the fifth. Okay, this is the very first example from this section. And let's say we wish to approximate P by some lower degree polynomial. So the approximation is good near x equals 1. Okay, so that is to say, let us first ask ourselves, where is this polynomial p centered? Zero, yeah, right? It's whatever's inside the power, and there's an x minus 0, so centered at 0. So if we just calculate P1, P2, P3 as is, will be a good approximation near 0. What we would like to do is come up with an expression that equals P, but is centered at 1, and then calculate the the D polynomials for this shifted version of P of X. Okay. So, is what we want. We want coefficients B0, B1, B2, all the way up to B5. So that we get B0 plus B1 times X minus 1 plus B2 times X minus 1 squared plus B3 times X minus 1 cubed plus, write this on the next line, plus B4 times X minus 1 to the fourth plus B5 times X minus 1 to the fifth equals P of X. Yeah. Okay. So how do we do this? How do we construct B0 through B5? Well, we have a formula for P. So let's see what happens. Consider P evaluated at 1. Okay, so P evaluated at 1 will just be B naught, right? I'm looking for coefficients such that this is all equal to P, and when I plug in a 1, all these X minus 1 terms will go to 0. So I have to have that the polynomial evaluated at 1 is our coefficient, B0. Okay. So then what do we do to find B2? Any suggestions? I don't want to just steamroll through this. What do you think? How might we go about finding B1?
Plug in 2 for the P of X, and then, like, I don't know, use algebra or something.
There is a way to use algebra. That's not quite it. But I think we will have a much easier time if we try to use calculus somehow. Any thoughts? Add V naught to what? Ah, okay. Not.
I'm trying to think of it in terms of like plus C and integrate, like,
Okay, okay.
I don't know if that's a moment.
Well, okay, let's think about this in a slightly different way. How was it that we were able to get this relationship out of P? It was because by evaluating at 1, we sent all these other terms to 0, and we're only left with the constant term, P naught. What can we do to our polynomial P so that we could isolate B1 as a constant term and have all the other summands go to 0? Say again? No, not quite. What happens if we differentiate P? I'm sorry. Yeah, exactly. Sorry, I cut you off there. Yeah, if we take the derivative of this expression on the left-hand side, the constant term drops out, and we just get B1 as the new constant term. And all the other terms in the sum still have a factor of x minus 1 in them. So we can differentiate and then evaluate at 1. And that value will be B1. Okay? Then differentiate and evaluate at 1. So this implies that P prime of 1 is equal to B1. Okay. So we can iterate this process, right? Again and again. But be careful, because as we continue to differentiate, we will get additional factors in the coefficients, right? Just by the power rule, right? When we differentiate the first time, we get a 2 out in front of B2, right? And a 3 out in front of B3, and a 4 out in front of B4, 5 out in front of B5, right? But as long as we keep track of that, we'll be fine. It's not going to be strictly as simple as the first 2 steps, but we still know what we're doing, okay? So let's work it out. Okay, so the double prime of x is equal to 2b2 plus 3 times 2 times b3 times x minus 1 plus 4 times 3 times b4 x minus 1 squared plus 5 times 4 times b5 x minus 1 to the third. Okay, which implies that p double prime evaluated at 1 is equal to 2b2. Okay, triple prime. What do I get here? Careful. Yeah. So I'm just going to leave it factored, just so we remember where that came from, right? From the successive derivatives that we did. Not strictly necessary, but I think perhaps slightly helpful. Okay, plus 4 times 3 times 2 b4 x minus 1 plus 4 times 5 times 3 x minus 1 squared. Implies the third derivative evaluated at 1 is equal to 3 times 2 times b3. Okay, just keep on chugging. Remember this notation for derivatives higher than 3, right? Little bracket exponent, the fourth derivative. Okay, so what do we get here? We got 4 times 3 times 2, 4 plus 5 times 4 times 3 times 2 times x minus 1. Fourth derivative of p evaluated at 1 is then equal to
4, 3, 2, 4. And finally, differentiating one last time, we just get that whatever here. The fifth derivative of p evaluated at 1. Well, actually, it's a constant, right? But 5 factorial p5, right? Of course, kind of building up to this all along, right? Okay, so now we have a bunch of relationships between our polynomial p, which we have 2 formula for, right? 2 formulae for, and the derivatives of this polynomial. Okay, so this is enough information to determine what these coefficients actually are. We'll complete that calculation tomorrow. All right. So have a good evening. And oh yeah, I also posted the solutions to the first quiz on Canvas this afternoon. If you didn't notice that, take a look. That won't necessarily be helpful for tomorrow's quiz, since it's not cumulative, but it is there for you. If you didn't get your quiz back, come up and see me. Where you go?
Thank you, Professor.